Hi guys. So today we're going to look at absolute value, and we're going to look at the graph of the absolute value function. So to start, just a quick review of what absolute value actually is. Absolute value is a number's distance from 0. So the absolute value of 3 is just 3. But the absolute value of -2 would be +2, because that's how far away -2 is from 0. Absolute value of 0 is 0. And then whatever is inside those absolute value bars, we basically treat like parentheses. So this would be the absolute value of -5, which is just 5. So the first thing we're going to look at is the parent function. So if you remember parent functions, those are the functions that all of our other absolute values are going to be based off of. Every other absolute value is just a transformation of this graph. So we're going to look and see what this graph looks like. Well, if I pick some x values to plug in, like 0, or 1, 2, or 3. The absolute value of 0 is 0. The absolute value of 1 is 1, 2, and 3. If I plug in negative numbers, the absolute value of -1 is +1, +2, +3. So if I go ahead and plot those points, you'll notice a pattern. An absolute value tends to be the one that's the easiest to remember the shape for, because it's called absolute value, and the shape looks like a V. So just reviewing some of our characteristics. So domain in interval notation would be from -infinity to infinity. Range from bottom to top. The lowest y value is 0. It goes up to infinity. This graph is increasing. So as we look left to right, the area of the graph where the y's are increasing then would be from 0 to infinity. Then the area where this graph is decreasing, so as we go left to right where the y's are getting smaller, that is from -infinity to 0. Extrema, this graph has a minimum value. This is a global or absolute minimum. It happens at 0, 0, which is the vertex. The other vocab we haven't talked about a lot so far is symmetry. So symmetry, you saw this on your quadratics in Algebra 1, we talked about the axis of symmetry. Well, the absolute value graph has symmetry as well, and the parent function specifically has symmetry on the y-axis. Now, this is going to mean something later on this year that we're going to look at, which means that this function is called an even function because it has that y-axis symmetry. So what we're going to do now is we're going to look at possible transformations. So this chart is probably going to look familiar. We've done it before. We're going to do it for a lot of our different functions. So if you remember f of x minus h, so if it's inside the parentheses, it's a horizontal transformation and it's backwards. So f of x minus h is going to go right by h. F of x plus h is going to go left h. That b value is going to be our horizontal stretch or compression. So if you remember, if it is greater than 1, it is a horizontal compression. It is backwards. And if it's in between 0 and 1, it was a horizontal stretch. And then if the negative was inside the parentheses, that was a reflection over the y-axis. So what we're going to look at is how these transformations look on an absolute value equation. So for an absolute value function that's shifted to the right, well, that's going to happen inside the absolute value bars. If it were to go left, that would also happen inside the absolute value bars. If it's a horizontal stretch or compression, that would be a number multiplied inside the absolute value and reflected over the y inside our absolute values. All right, then we're going to look at vertical changes. So anything that happens outside of the parentheses, which will be outside the absolute value bars. Those are our vertical transformations. So this one is going up k. This one is going down by k. If a is greater than 1, that's a vertical stretch. If a is in between 0 and 1, that's a vertical compression. Negative on the outside, that will reflect over the x-axis. So what these are going to look like on absolute value, again, it's going to happen outside of that function. So the absolute value of x plus k would be up. minus k would be down. If that number is multiplied on the outside, it is a vertical stretch or compression. And if there's that negative, that would be a reflection over the x-axis. If you were to see all of these transformations, it would have this form. Now, one thing to notice about this form, that b value is factored out. That's something we're going to get in the habit of doing, especially for absolute value, because with some properties for absolute value, it's going to make it a lot easier. The other thing on this equation, hk is going to be the location of the vertex. All right, hk is going to be the location of the vertex. All right, so let's look at a couple examples. So the first thing we're going to do is we're going to find our transformations, so things that we just talked about. So this graph has been shifted right 2, and this graph has shifted down 3. Since our vertex is hk, that means our vertex is going to be at 2, negative 3. So I'm going to start by plotting my vertex. Then from this point, we need to consider what the parent function looks like. Well, the parent function, typically from that point, so from the vertex on the parent function, I went over 1 and then up 1. I went over 2, up 2, right 3, up 3. And again, that's how this graph moved from the vertex on the parent function. Well, this graph, it's going to have the same thing. It has not been reflected, it has not been stretched, it has not been compressed. So from the vertex, we're just going to go over 1, up 1, over 2, up 2, over 3, up 3. And since this graph has symmetry, we're just going to do the same thing on the other side. And now I can see my graph. Once my graph is plotted, we'll go ahead and find our domain and range. And you'll notice a trend here on domain. All of these absolute value functions will have a domain of negative infinity to infinity. Then my range, the lowest point is negative 3, and it goes up to infinity. All right, so let's look at the next one. Again, first thing we'll do is list the transformations. So that negative out in front, that is a reflection over the x-axis. That means this graph is going to open down. All right, this also has been shifted up 2. Vertex is hk. Well, there is no h, and k is 2. So this graph is going to have a vertex at 0, 2. It's going to open down, but it has not been stretched or compressed. So it's still going to be from that parent function over 1, down 1, over 2, down 2, and over 3, down 3. And we're going to follow that same pattern on the other side. Our domain then is from negative infinity to infinity, and our range is from negative infinity until the y value of 2. All right, so now let's look at some that have some stretches and reflections. All right, so this graph here, that 2 out in front, that is a vertical stretch. And this graph has shifted to the right 1. The vertex is hk. My h is 1. There is no k. So the vertex here will be at 1, 0. But again, this graph has been stretched, so it's not going to look the same as the parent function. The parent function from the vertex went over 1 and up 1, over 2, up 2, over 3, up 3. Well, since this graph has been stretched vertically, instead of going over 1, up 1 from the vertex, we'll go over 1 and up 2 from the vertex. From the vertex, I'll go over 2 and up 4, and over 3 and up 6. Because we're stretching it by 2, it's changing those y's. And again, this is from the vertex, how it's going to change. The reason we don't need to worry about stretching or reflecting the vertex is because originally the vertex is at 0, 0. And if you multiply that by anything, it's not going to change it. So the vertex is only affected by those shifts. So then from the vertex, over 1 and up 2, over 2 and up 4, over 3 and up 6, and then we have our symmetry, and we have our graph. Now the other way that you can graph these, and probably how we're going to do it most of the time because it's a little bit easier, what you'll notice if you look at just this line right here that I just graphed, the slope of that line, I was going up 2 and over 1. So that line has a slope of 2. On the other side, it has a slope of negative 2. Well, that slope is just that number that's out there as my stretch. So whatever the value of your stretch is, that's basically going to be the slope of your graph. All right, let's go ahead and find domain. That is not changing. Range lowest to highest point. So that has a y value of 0, and then it goes up to infinity. All right, let's try this next one. So we'll start by listing transformations. So this graph has been reflected over the x-axis. All right. This graph has been vertically compressed by 3/4. It's gone left 1 and down 2. So my vertex is going to be at -1, -2. Because it's been reflected over the x-axis, it's going to open down. And then that slope is going to be that 3/4. So down 3 over 1, 2, 3, 4. And then same thing on the opposite side. And I have my graph. Write my domain. And then range lowest to highest. All right, so the next thing we're going to do is we're going to look at some graphs that use some of these properties of absolute value. So we'll also revisit these when we get to solving, but 2 of these properties are going to make the horizontal transformations a lot easier to graph. So looking at E, the first thing we want to do, we want to put it in that form that we wrote, which means I need to factor out whatever is attached to that x. So that means I'm going to take 2 and factor it out. Well, if 2 comes out, if I'm factoring that out, I would be left with x minus 1. So now from here, I'm going to apply one of these properties. So what this property right here tells me is that basically anything that's multiplied I can separate. So I can rewrite this absolute value here. I could rewrite that as the absolute value of 2 times the absolute value of x minus 1. Well, the absolute value of 2 is just 2. So really what I did, after I factored that 2 out, I can just move it to the outside of that absolute value. Now I don't have to worry about that being a horizontal compression and having to graph a horizontal compression. I can graph this exactly the same way as I did in the example previously. So this graph actually has a vertical stretch. Now if you want to say a horizontal compression, that's totally fine. It's just a little bit easier to graph it when we move it out this way. And then we can tell it's been shifted to the right one, which means it has a vertex of 1, 0. So I'll go to my vertex, slope of 2, or symmetrical on the other side, and there's my absolute value graph. We've already done our domain and range, and that's it. All right, so looking at F, again, same idea. Whatever is in front of the x, I need to factor out. So that negative needs to get factored out, which means I really have x minus 2. Well, using the other property of absolute value that's listed here, the absolute value of a negative is just the absolute value of that number. So if there's a negative inside that absolute value and we've factored it out, I can just drop it. And if you think about what's happening to your graph, if you reflect the absolute value function over the y-axis, it's not going to change it. And by factoring it out, we'd be applying that transformation first. So now it's easy to see my transformations. This has a vertical compression. It's been shifted right 2 and down 1. So our vertex is at 2, -1. And then it has a slope of 2/5. So up 2 and over 5 will go off the graph slightly. And there's my absolute value function. Domain has not changed. Lowest y value is -1. And then it continues to infinity. All right, so again, it's very important anytime you see something inside those absolute value bars, if it's attached to the x, we need to factor it out. Then if it's some constant, we can just move it to the outside. If it's a negative, we can drop it using those absolute value properties. Now, this is not going to work for every function that we use, but it is going to work for these absolute value functions just because of the nature of their properties. All right, so now we're going to work backwards. We're going to be given a graph and we're going to write the equation. So in order to write the equation, we need to know what's the vertex, we need to know what direction it opens, and then we just need to know the slope coming from the vertex. Well, this graph has a vertex of 3, -2. So the form that this goes in, if you remember, It's A, absolute value, B, x minus h plus k. So A is going to be that slope. It opens up, so it's positive, and then that slope up 2 over 1. So this would be 2, x minus 3 minus 2. Now, if you wanted to, you also technically could write this as 2 parentheses x minus 3, and it's going to give you the same graph. So you could write those either way, but typically you just tend to see this one more often. It's a little bit easier for us to write. All right, looking at B, again, we find the vertex. The vertex is 1, 3. This graph opens down, which means I'm going to have a negative out in front. The slope is 1. So this would be negative x minus 1 plus 3. And that's it. Again, if you wanted to, well, I guess in this point it's 1, so it wouldn't really matter where that value is. But that negative does have to be on the outside. We can't just move that negative in there because, again, that would be a different graph. All right, so the last thing we're going to do is we're just going to write these equations just from words. So one thing that we're going to look at here also is order. So the first one, it says it's an absolute value graph. It's been shifted right, reflected over the x-axis, and then it's been vertically shifted up 2. So to show that it's been shifted right, that would be inside the bars, x minus 3. Reflecting over the x-axis would be a negative out in front. And then after that, we're going to shift it up 2. Well, that is the normal order that we are used to following. We multiply before we add and subtract. So I need to put that plus 2 on the outside. All right, let's look at our next example. Shifted left 2. So inside the absolute value bars, x plus 2. Shifted up 4. But then it is vertically stretched by a factor of 2. So that is not the order that we are used to applying. So what we need to do is we need to consider what's happening. I've done these two transformations first. Then I have stretched it vertically. So what I need to do then is I need to take the entire function that I have and then stretch it by 2, which means that I really have 2 times the absolute value of x plus 2 plus 8. And really what we're just trying to understand here is that the order we apply these transformations in matters. If I stretch by 2 and then I shift it up 4, it's going to look different than if I shift it up 4 and then I stretch it by 2. It's going to create 2 different graphs. All right, then this last one deals with multiple horizontal changes. So if there's a horizontal compression of 1/2, first of all, we need to remember that's not going to be a 1/2 in the equation. That's going to be a 2 inside the absolute value bars. Then it says it's followed by a shift left 2. So if the horizontal compression comes first, in order to multiply first, we have to have factored it out. So that means I need to have parentheses, and then it's going to be x plus 2. And that's it for our absolute value graph. So again, just pay attention to your transformations. Make sure you can factor out anything that's in front of that x inside the absolute value bars.